So hello, my name is Rudi Pendavingh. I'm here to talk about my research interests. So let's go. So I am exceedingly old, so I have a long history of doing mathematics. Um, but it's safe to say that most of the things I've done fall in combinatorics, geometry, and algebra. So the type of objects that I handle on a day-to-day basis are graphs, matroids, polyhedra, entropy, finite fields, so modular functions, convex sets, and so on. And yeah, what do? I count, I optimize, I reconstruct things, I enumerate them, I schedule, I design, and so on. So I prepared not all the problems I've ever worked on, but a selection that sort of shows you the complete range. So in my earliest days as a researcher, I worked on spectral and topological graph theory. So a graph can be considered a space, a one-dimensional space with little nodes, and it supports Schrödinger operators, discrete Schrödinger operators. Now, the extreme behavior of these operators tells you something about the topology. So the maximum multiplicity of the first eigenvalue is exactly the number of components. And then the hope is that the maximum multiplicity of the second eigenvalue will also tell you something interesting. And indeed it does. It can exactly tell you whether the graph is planar, for example, or linklessly embeddable. And now, the long-standing hope is that you can learn something about a coloring number from the topology. There's the four-color theorem. So this spectral invariant raised hopes that that we could understand that conjecture or that theorem in a better way via the spectrum. But of course that didn't work. But we learned a lot about the relation between spectra and topology. Now another thing that I worked on around the same time was classic graph optimization, finding an optimal routing. So in the picture you see something that is called a bi-branching, a collection of arcs in red, so that every node under the line has a path to a node above the line, and every node above the line has a path from a node below the line. Now if you give every edge a cost, then the question is, how can you find a bi-branching of minimal cost? It turns out, so what mathematicians do in that case is something very strange. They take the set of subsets that they're interested in, like one subset would be a subset of the edges, which forms a bi-branching, and they encode them as vectors, 0, 1 vectors, and then they try to do linear optimizations on the convex hull of those vectors. And that only works if you have a very nice description of that convex hull. And even then, it's still a problem to arrive at a good algorithm. Now, a nice polyhedral description of that particular set was available, and then I learned how to create a nice algorithm from that. So I don't think I work on optimization problems that much today, but I still teach about it. So all this stuff about linear optimization and polyhedra is there every day still. So here is a problem that I spent quite a bit of time on. So a matroid is like a combinatorial geometry. So it tries to capture the structure of linear independence and algebraic independence. Not only tries, it actually succeeds in capturing that. There's many more matroids than those that come from vectors or field extensions. And this raises the reverse question: if I give you a matroid, can it actually be represented as vectors or over a field? And the classical way to answer this question is by pointing out certain substructures that you can't have when the matroid is representable. But another approach is to try and decorate the matroid with certain symbols that sort of foreshadow its representation and that have a structure that is like the representation. And it turns out that if you try to decorate a matroid in this manner, you immediately learn something about its potential to be represented in many different ways. So this type of research led to partial fields, hyperfields, valuated matroids, and all that. Now here's a small problem perhaps, but still interesting. To me it was, at least. So, so to biologists, it is an interesting problem. What is the tree of life? The kind of data that they usually have is how that tree looks like on certain subtrees. So they might be able to say that on the four species B, C, E, and F, the subtree of the tree of life must look like the red tree that is indicated. And if you know these subtrees for all possible four tuples, then you are probably able to reconstruct the whole tree. One way of doing this, it turns out, is via linear algebra. You can associate trees with certain subspaces over Z of 2, and then each possible input tree quartet gives you an equation, and then the subspace associated with your tree is exactly the solution to the equations that you get from the subtrees. So that gives you a method for reconstructing trees. Counting matroids. Yeah, that is a nice problem. So matroids have an axiomatic description, and that means that you can't just insert certain parts into it. The whole thing has to hang together in an organized manner. But since you can't just switch parts of it on or off, it's also difficult to count their number. It was actually a very long-standing open problem, how many matroids there are on a fixed ground set. So when we considered this problem, we eventually found a way to give upper bounds on this number by showing that every matroid can be described in a very concise way. And if you can show that every matroid on a certain ground set has a description with only k bits, well, then you've shown that there's at most 2 to the power k of them. So that brought me in a beautiful world of entropy compression algorithms, and it was nice stuff. So here's another small problem that I worked on recently. So in darts, you can. Now I'm suddenly out of it.
That's okay. We can cut this out.
Yeah.
Take
Okay.
a break.
What do I want to say about this? You don't know this. Why not?
I know darts, but
Okay, let me think for a moment. This was my last slide.
to hit the right solution.
So finally, here's a problem that I worked on more recently, scheduling darts competitions. So in darts competitions, they take the form of a sequence of knockout tournaments. So in a knockout tournament, you start out pairing up the contestants, and then the winners of those pairs, they are again paired up until you end up with just one winner of the evening, usually. And then after a sequence of such knockout tournaments, the winner is declared according to some scheme. Now, it's not considered fair if a certain pair of players meets on a very high level each time in every one of these tournaments. So a fair competition is a competition where the number of times a pair of players meets on a certain height in this tournament is more or less the expected amount of times that you would meet. And it was not easy to create a schedule that is exactly balanced in this manner. But it turns out that finite fields had the exactly right algebraic structure to create a nice schedule for several nights for your darts competition.